Welcome back to the Turtberg Broadcasting Network. Today's video brought to you by, well, actually, it's pretty much just me. Anyway, today's video is on magnetic fields. In particular, we're dealing with magnetic fields having to do with current carrying wires. So pretty much every problem in this section is got to do with a wire. So in this case, say we've got a wire and there is a current in that wire. I don't know, we could say an I of 2 amps. But anyway, just some form of current is all we're looking at. Well, before we get into looking at this wire and even looking at this equation that I've got written up here, I want to go back to 10th grade. Wasn't that a great time? Back in the day, pimples, the whole 9 yards. Anyway, north, south. We did a lab where we took a magnet and we laid it on the table and we put some dots around the around the magnet. I'm sure some of you remember it. And then we come back and we put a compass right next to it, and the compass would line up and point to the dot, and on the other end we'd put a dot there, and then we'd slide the compass around till we had a bunch of dots going everywhere, and it probably made a pattern that looked like this. Whee! It's a beautiful little magnet. But anyway, so hopefully maybe you've done a lab like that before. So now let's go back and take a look at this wire. So I want to pretend like we've just took this wire and we've kind of jammed it through a big piece of cardboard here. So we've jammed the wire right through a piece of cardboard. And so this is a solid piece of cardboard here. Big thick piece of paper, something. And I want to do the same thing I did with 10th grade. I want to put a dot somewhere on that piece of cardboard. And then I want to lay a compass right up beside it. And I want to come back and I want to put a little dot on the other end of that compass. And then I want to move it. And I want to keep lining it up and keep putting dots. Well, this will be something cool. It will end up, the dots you start making on the paper will end up making a circle. So the dots will actually form a pattern on there. Dun, 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 dun. So you'll see this circular pattern, which means the magnetic field created by a wire, it actually makes this circular magnetic field around the wire. Now, this chapter involves two things. One, you being able to measure how strong that magnetic field is. Well, that's easy. We have an equation for it. Go ahead and take a look at it. The equation itself, if we want to know how strong the magnetic field is around the wire, mu O is a constant called the permittivity of free space. Man, that's sexy sounding. Anyway, that's this mu O. It's a constant. It doesn't change. Now, as for me, I kind of like to do this. I don't have my Casio FX calculator out for something. Where is it? Oh, Casio. There you are. I like to go ahead and do this. 4 times 3.14, 4 pi, 12.56. When I'm working these problems out, I like to go ahead and instead of putting 4 pi in my calculator, a lot of times I'm prone to go ahead and putting into my calculator 12.56. I don't know. It just depends. It's up to you on that case. But anyway, moving on. You know what I stands for. That stands for current measured in amps. And the only thing left is that R. And that R is just representing radius. It's representing how far you are. So if this is the wire, it's representing how far some point is from that wire. And that's all R is, and it's going to be measured in meters. So there's our basics for these problems. Now, one of the things they're going to ask you to do, just like a magnet has a north and south pole and you have a direction, well, the same thing is going to be true about that magnetic field around. In other words, when you lay the compass there, north is actually going, it's going to actually align north and south, which means that magnetic field has a direction. So how do we find this direction? Well, and this is going to be one of the first questions anybody asks you. Right hand rule number 2. This is going to be one of the first questions you get asked. Now, you've probably already done a right hand rule number 1 by this point. That's in the first part of this chapter. Right hand rule number 2 is pretty different. All you're going to do is take your hand, there's your fingers. Hello. Big, long, weird looking fingers with a fat pinky. But anyway, all you're going to do is take your hand and you're going to wrap it around a conductor. Now, your fingers represent magnetic field and your thumb represents current whenever you do this. So all you've got to do is say, for example, if this was a wire, I want you to take your hand and I want you right now to virtually take your hand and wrap it around my wire. So there's my thumb pointing that way. And now wrap your fingers around that wire. And that's a hideous looking fingers. But anyway, wrap your hand around that wire. And I want you to notice something. One, my thumb's pointing that way, so that's telling me my current in that direction. When you wrap your hand around this wire, my fingers on this side, my fingers are going into the page. I draw those little X's to represent that. And if you're at this point watching videos, you should already understand notation in terms of magnetic fields. But my fingers are going in on this side, and that's why I draw the little X's over here. And if you wrap your fingers around, they'll curl all the way back around into your palm, which means on this side, I draw little dots to represent the magnetic field is coming out of the page on that side. And this is how you do right hand rule number 2. And you've got to be able to do right hand rule because that's going to help you draw all these vectors you're about to do. Well, I went to WebAssign, and let's look at this first question in WebAssign. All it asks you to do is in each of these scenarios, it wants you to find current. So like, for example, in A, all it wants you to find is the current going right or is the current going to the left in that wire. Well, take your hand and wrap it around. So I want you to get your right hand out. Right hand ready. Now take your right hand and wrap it around that wire in such a way that your fingers go in on that side and your fingers come out on this side. Well, in order to do that, you're going to have to lay your hand, there's my thumb, just like this, and coil my fingers around that wire. Which means the current in this problem is going towards the left. And that's how you do this right hand. And it's really hard to explain via just a pen on a screen, but that is the way. So now do the same thing on this side. Let's go ahead and do this one. This guy, your fingers need to go in, and this is where they need to come out on that side. So you got to lay your hand on that wire in such a way that your fingers are going to match that. Well, take your thumb and now wrap your hand around that wire. Oh, that's actually probably the best looking hand I've ever drawn, which isn't saying much. But my thumb is pointing that way, so that's the direction of my current in that case. Now, let's do this very last one that's up here. Now in this one, the wire is actually perpendicular to the page. So my wire, I was drawing red on a red dot. So the wire is actually perpendicular in this case. So here's what I'm going to do. My fingers are going this way is what it's saying. So how could I lay my right hand so that my fingers ran counterclockwise? Well, I'm actually looking at my hand right now, and my thumb is pointing straight to my face, which means the current is running out of the page. And hopefully that gets you a little primed up on this right-hand rule stuff. 9 minutes in the video. And let's do one example using this, and then we'll make a second video doing more examples of it. But here we've got a problem, and it's about a lightning bolt. Here comes my lightning bolt. And to do this problem, we're going to pretend that the lightning bolt is nothing but a wire. Matter of fact, it's a wire that has a current in it of 1 times 10 to the 4 amps. And now we can come back, and it says it wants to know how strong is the magnetic field at a point that is 180 meters away from the bolt of lightning? That's easy. We're just looking for magnetic field. So all we're going to do is B equals mu O, permittivity of free space, I over 2 pi r. And so I'm just going to plug in. I already know what mu O is. It's probably in my calculator already. 1 times 10 to the 4 divided by 2 pi, and r is 180. And I'll actually show you some quicker ways in other videos of doing that calculation. But anyway, let's just plug it into the calculator at this point. So let's bring up my calculator. Mu O is 4 pi 10 to the negative 7. I'm just going to go ahead and write 12.56 10 to the negative 7. And I don't have any idea why I'm putting it in that way. Here, let's do it this way. So 12.56 10 to the negative 7 times 1 10 to the 4 divided by 2 times pi times 180. And my answer is, look at this, 1.11 times 10 to the negative 5 is my answer in this problem. So 1.11 times 10 to the negative 5, and if you haven't learned it yet, the unit for a magnet is a Tesla. There's also a unit called a Gauss. It's an old school unit, but anyway, a Tesla is what these problems, the SI unit, is. So there is my answer to this question at this time. If we take a look, here's their answer, and they've got it in micro Tesla, so thus they moved it one more place. 10 to the negative 6 gave us 11 micro Teslas. Alright, so that's where I'm going to stop this video. The next problem is going to be probably what's the harder one. How do you treat with 2 wires? And that's where we'll start the next video.